Now, dear students, the next topic, that is kinematics of rotational motion about a fixed axis. Okay. Now, in this one, we will derive the kinematic equations for the rotational motion which is with constant angular acceleration, just like we derived the equations for the translational motion, right? Now here, consider a rigid body which one is rotating with respect to a rotational axis which is the z axis as shown in the figure. Now consider any one constituent particle of this particular body, and when the body is executing rotational motion, the particle will execute the circular motion. Now particle is executing circular motion in xy plane. Suppose at a particular instant, so we consider the position of the particle at P, that is suppose time t equal to 0. So with respect to x-axis we consider as the reference axis. So with respect to x-axis, its angular position is theta 0, and at that time, means that time t equal to 0, suppose its angular speed, that is omega 0. Then at some instant t, the angular position of the particle, that is theta, means particle is displaced from P to Q. So with respect to x-axis, suppose the angular position, that is theta, and its angular speed, that is omega. Here the body is executing rotational motion with constant angular acceleration. Now, as per the definition of angular acceleration, we can say angular acceleration, that is change in angular speed upon time interval. So we can write alpha, that is omega minus omega 0 upon t minus 0. So we can write omega minus omega 0, that is equal to alpha t, or we can write omega, that is equal to omega 0 plus alpha t. So see here, this particular equation is exactly like the equation of translational motion with constant linear acceleration, that is v equal to v0 plus at. Now here we can write the average angular speed, that is the initial speed plus final speed divided by 2. Here we can take average angular speed in this manner only when the angular acceleration is constant. Be careful, otherwise directly you can't take the average like this. Okay. Now average angular speed, that is omega bar equal to omega plus omega 0 by 2. So we can write the angular displacement, that is equal to average angular speed into time interval. So angular displacement, now at time t equal to 0, particle is at P, at time t equal to t, it is at Q. So displacement, that is theta minus theta 0. So here we can write the angular displacement theta minus theta 0, that is equal to average angular speed omega bar into time t. Average angular speed, that is omega plus omega 0 by 2 into t we can write. Now here substitute the value of t from this equation. T, that is omega minus omega 0 upon alpha. So theta minus theta 0 equal to omega plus omega 0 by 2, this one, and t is replaced by omega minus omega 0 upon alpha. So in numerator we can write omega square minus omega 0 square. upon, in denominator we can write 2 alpha. So we can write omega square minus omega 0 square, that is 2 alpha into theta minus theta 0. And see, this equation is exactly like the equation of translational motion, that is v square minus v0 square equal to 2a into r minus r0. Now again concentrate on this particular equation, and in this equation substitute the value of omega from the previous equation. Now see here. Now in this equation, theta minus theta 0 equal to omega plus omega 0 by 2 into t. Substitute the value of omega. That is omega 0 plus alpha t. So we can write resultantly, therefore theta minus theta 0 equal to omega 0 plus alpha t plus omega 0 by 2 into t. So here we will get omega 0 plus omega 0, that is 2 omega 0 by 2. So 2 will be cancelled. So that is omega 0 t. And alpha t by 2 into t. So half alpha t square. So we can write therefore theta minus theta 0 equal to omega 0 t plus half alpha t square. And this equation is exactly like the equation of translational motion r minus r0 equal to v0 t plus half a t square. Right? So these are the kinematic equations for the rotational motion with constant angular acceleration. Clear to all of you?